Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Done. This is an extended and elaborated version of the presentation that he gave at IWPT, apparently, where I was amazed that he got through 52 slides in 25 minutes, and that the questioning at the end demonstrated that people actually had kept up with them and really absorbed it. So that's quite an accomplishment. Young is a student at Penn, although he's also doing a lot of collaboration with people at ISI on things to do with K-best parsing and also K-best approaches in general for things like machine translation and all sorts of things that are near and dear to our hearts. So his schedule is pretty full for today with the MSR fellowship interviews, but he's sticking around tomorrow to talk with additional people, just some sort of sucker for punishment. And if you'd like to sign up with him, just talk to me afterwards.
Thank you, Simon. You basically told the guys what this talk is all about, so I don't have much to say. This work is about K-best parsing, basically meaning fast and exact K-best Viterbi parsing algorithm. And since I know some of you guys are working on machine translation, so I'll also talk a little about, about K-best translation, how to apply these K-best parsing algorithms in syntax-based machine translation. So first of all, what's K-best parsing? Well, basically it means given a natural language sentence, say I saw a boy with a telescope, which is ambiguous, you at least get two readings. And I not only want the first best interpretation, but also the second best and the third best and through the case best. So that's the task of getting the top K interpretations or structures for a given sentence. That's K-best parsing. So before I talk about any technical details, I first want to convince you that it's not an easy task even for human beings, because my advisor, Arvind Joshi, when he was awarded the Benjamin Franklin Medal, he was asked to give a talk, basically introductory talk to high school students, those local Philadelphia kids, because the Benjamin Franklin Association want the kids to understand what Dr. Joshi is doing and what's natural language processing, what's computational linguistics. But that's really a hard task to teach the kids. But Joshi found a smart way to do that. Basically, just speak a sentence and let those kids draw whatever they have in their mind instead of telling people what it means in language, because the kids at their age are much better at visual abilities. So there's actually one kid got this for I saw her duck. And then the next sentence, I eat sushi with tuna. The same kid got this. So this is a typical PP attachment problem, ambiguation. And what can we say? Well, basically, your K-best parser is not accurate. There's no reason or no situation that you can get this interpretation to be your top interpretation for this sentence. So you didn't improve your K-best parser. OK, back to technical stuff. So why is it important, problem? Because we often have NLP as a pipeline of several stages or several phases. Say you first do part of speech tagging, then parsing, then semantic interpretation. And that's often the case that the first best from one stage is not guaranteed to be optimal in the future phases. And what people do is to postpone disambiguation by propagating a K-best list instead of just propagating a first best answer to the next phase. So that's what people do between syntactic parsing and semantic role labeling, for example. Well, it's also true that it's widely used in discriminative training, recent methods of machine learning, especially in reranking and minimum error training or perceptron like online learning. Basically, here we use a K-best list, the top K interpretations, to approximate the full set of all interpretations, which is usually exponentially large. Say the set of parses for a given sentence is exponentially many, right? But but most of them are crap. So just use, like, say, top 100 parses to approximate the whole set. And the bet is you get the majority, the probability mass right. So it's a good approximation. So what people do in previous work, well, the simplest and earliest approach attempt to do that is in Collins' Reranking paper, where he basically turned off dynamic programming totally, meaning no two items are considered, no two interpretations are considered equivalent, so that he keeps all the derivations in the chart, which means that is an exponential algorithm. How to make it work in practice? So he has to do very aggressive pruning to make it tractable. But as we will show towards the very end of this talk, this pruning has very bad effect on the quality of the output. So Chaknian and Johnson did something better recently, which is multicast, coarse to fine-grained, but it's still not exact k-best. So ours is exact k-best and fast algorithm. But it turned out that there is an earlier paper, which is largely unknown to our community, by two Spanish guys, Jimenez and Marcel, which presented basically very close algorithm to very much the same to our final algorithm, although we have an improvement. And they tested it on a tiny grammar. So what our work differs from their work is that, first of all, we formulated our algorithms on the very general framework of directed monotonic hypergraphs, so that all parsing algorithms that can be captured by this framework can be applied for our algorithm. And then we have four algorithms, four k-best algorithms, each of which improving the previous one a little bit. And finally, we get algorithm 3, which is pretty fast. And we present experiments on state-of-the-art natural language systems, one on the Collins-Spickel style parser, which is a tree-bank parser, and the other on the CKY style decoder by David Chen. So first of all, what's a hypergraph? What's the difference between a hypergraph and a conventional graph? Well, the only difference is that in a graph, an edge links two vertices, and in a hypergraph, a hyperedge links several vertices to one vertex. And this is very similar to the deductive specification of parsing algorithms, where you have antecedent items. And if you have derived all these three antecedent items, then you can derive the consequent item. So this deductive rule is captured as a hyperedge in hypergraph. And so if you're familiar with CKY, this is the CKY deduction. And for example, you can have MP, VP, and you can derive an S. This is an instantiation of the rule, of the deductive rule. And this instantiated rule is basically a hyperedge, where the items in the chart are vertices in the hypergraph, and this deduction is a hyperedge. So this way, hypergraph can be thought of as a compiled version of the instantiation of deductive specification of parsing algorithms. So that's what Klein and Manning did for logical deduction, and it's also the same as the notion of packed forest in our field. So, for example, get this sentence: I saw a boy with a telescope. There are two interpretations, and how do you compactly represent both of them? Well, that means, do you have a method to use polynomial space to represent exponentially many parses, right? And that's what packed forest does, basically combining the two equivalent items, basically because these two VPs spanning the same range of indices, and they are both VPs, so they are equivalent. And that's the only ambiguous part in this sentence, and that's packed forest. So we all know packed forest, but what if we just rearrange these nodes a little bit, and then we get a hypergraph? So now the nodes are vertices, and these links are hyperedges. So basically, it's really nothing new. But people also do, in practice, weighted deduction, like probabilistic context free grammars, or as such. So we also need to formulate weighted deduction into weighted hypergraphs. So, well, it's also very straightforward. In weighted deduction, you have, say, a weight or the score, the best score the best derivation of this item, B and C, and then if you derive the item AIK, then you know the resulting weight is the result of applying the weight function f to the weights of the antecedent items. And in CKY, it's really simple, just B times C times the probability of this rule. But in general, in a weighted hypergraph, suppose you have a deduction, and you have a weight function for each deduction, then you can represent it as a hyperedge, but you just have a weight function in this hypergraph. So a weighted hypergraph has a set of vertices, a set of hyperedges, a special vertex called target, basically meaning the goal item. Say in CKY it's S of 1 to n. Basically, if you recognize S for the whole sentence, then you are done. And R is the weight set where your weights are from, and we refer to be a total order set so that we can compare derivations. And your hyperedge is the set of antecedents, that's tails, and head of the edge, that's the consequence, and a weight function. So if you have the weight function for this row, and basically have the same for this hyperedge. So that's formalizing the NetHof's weighted deductive system. But weighted hypergraph in this way is a little bit more flexible or general than weighted deduction, in the sense that we can have different weight function for different hyperedges. Whereas in the weighted deductive system, all the weight functions are in the same class, say A times B times C times the probability of this rule. So we can have ad hoc weight functions for ad hoc instantiation of deduction, which is a little bit more general. So any questions so far? Sure.
So this is no longer a CFG then?
This can be more than CFG. Say you have a tag, you can still represent, you have a tree adjoining grammar parser. You can still represent them as a weighted deduction system, deductive system. And any parsing algorithm that can be captured as a weighted deductive system can be formulated as a hypergraph search problem.
But still, if you're able to wrap everything under A in a single score, that sort of suggests a CFG formalism.
Exactly. So this is a very good point. So for hypergraph, you can represent it as a CFG. But this CFG is different from the original grammar CFG because you intersect the CFG with the sentence, basically with a DFA representing the sentence. So that's exactly the same as the Bach-Hillel intersection approach, where you intersect the CFG with a DFA, then you still get a CFG, because CFG intersected with regular grammar is still CFG. And the parsing can be viewed as a generation problem in that intersected CFG. So there's two different CFG. So Bob, what's that?
Yeah, I'm sure you're going to get to this in a minute, but at this point, what I'm wondering is what score do you put on a hypergraph if you have? Oh, I guess it's yeah. What score do you associate not with a node if there are two different hyper edges that have that node as their target?
Yeah, you take the best of them. You take.
Okay, so you
yeah.
use the Viterbi.
Yeah, I use it, but I'll cover that in several slides.
There might be other applications where you want to take the sum, I'm sure.
Yeah, exactly. So here we only care about comparison, basically take it better. But in semi-ring, we can have the sum operator, which you can take the inside, for example, right? So here we only care about the optimization problem. So we have the total order set. So we talked about the weight function a lot, and we have a very critical assumption that all the weight functions in our framework must be monotonic on each of their arguments. What does that mean? For example, in CKY, f weight function is b times c times the probability of this rule. And this is, of course, monotonic on both b and c argument. But in general, this requirement formalizes the optimal subproblem property in dynamic programming. That is, if you want to apply dynamic programming, you have to have the optimal problem property. That means if you can decompose a large problem A into B and C subproblems B and C, and if you have something better for the subproblem B, so you have a B prime, which is better than the original solution, then by applying the monotonic weight function f, you can always get something better for A as well. In other words, if you claim this is the best solution for A, then the solution for B and C must also be the best for the subproblems as well. So that's the optimum subproblem property. Now, as we have hypergraphs, now the k-best problem are very easy. Just basically find the top k derivations of the target vertex T. In CKYT, it's very easy. Another critical assumption is that we only care about acyclic hypergraphs, so that we can have a topological sort among the vertices, and we just proceed along the topological ordering. We know that CKY, of course, is acyclic, and a lot of the parsing algorithms are acyclic. So now we come to algorithms. So we have 4 algorithms, from naive to lazy. But before I talk about any k-best algorithm, I first want to have some basic idea of generic first best Viterbi algorithm. So we call it generic Viterbi algorithm, but it's basically extending the original Viterbi on the hypergraph. So basically you have a topological sort. First do a topological sort on the hypergraph, and then proceed in the topological ordering. Basically for each vertex, for each incoming hyperedge, you take the result of this hyperedge using the weights of the antecedent items F and B. A and B are the weights of U and W. Just to remind the intuition behind it, think about CKY, these U and V and U, V, W are items in chart. So if you have another hyperedge, you take the better of this. That's what Bob says. And you have more, you take the best of all these results of all these hyperedges. And that's the linear, that's the complexity linear in the number of hyperedges, because you visit each hyperedge once and only once. And as a special case, CKY for Chomsky normal form is cubic times the number of productions. And this number is exactly the number of hyperedges in the hypergraph. And that's why CKY is cubic. So CKY being a special instance of the generic first best Viterbi algorithm. Okay. So, well, that's really nothing new, because dynamic programming has been around for more than 50 years. So what I presented before is really nothing new. But what these guys, the inventors of dynamic programming, doesn't know is k-best dynamic programming algorithms. Well, the easiest approach that extending the first best Viterbi to k-best is simply replace the weight A and B to be a vector of k guys. And if you maintain them to be sorted, then A1 will represent the best derivation, the best weight for A, and AK, the k's best derivation weight for A. Okay, so now A's and B's are both length k. Now the question is, what's the result of applying the weight function f to these two vectors? Well, the weight function is not defined that way, because weight function is defined only on 2 numbers. Now you have 2 vectors. Well, if you have two vectors, and all the possible AI and BJ is a possible solution, is possible element for, when applying f to A's and B's. So basically, you have k-square possibilities, and then you want to select the top k among them, because you're only interested in the k-best derivation, the top k derivation for this v, so you don't need all the k-square guys, right? So basically, you enumerate all the k-square guys first, and then do sorting or selection, basically, to get a top k. So that's what we say multi-k equal to top k of all the AI bj, right? Okay, so that means you have at least k-square amount of work to do. But that's not all, because when you have another hyperedge incoming, then you basically want to take the better of these two. But now you have k guys here and k guys here. And now this step is easier, because you know these k guys are sorted and these k guys are also sorted. So just take the top k among the 2 k guys. That's linear. You can do a merge sort like thing, which is linear. But simply computing the multi-k is k squared. So this is no better than k squared. So that you have that means you have a k square overhead for each hyperedge, right? So your overall complexity is k squared times e. This is really bad, because in practice you want k to be very large, say 1,000 for translation, or for translation you may want 10,000. For parsing, you may want 100. So that means this k-square will kill you. Any questions? So we can do something slightly better, because the worst thing about the previous algorithm is you enumerate the k-square guys first, but you really don't need to do that, because you only need the top k guys. And remember that A's and B's are sorted, and the void function f is monotonic. That means A1, B1 must be the best of all these k-square guys, right? And then what about the second best? Well, it must be either A1, B2, or A2, B1. It cannot be anything else, right? And then what about the third best? So here is a demo. So you have 4 guys for A, 4 guys for B. You know that this guy, A1, B1, must be the first best. And the second best must be either these 2 guys. And since 24 is better than 20, you know, this guy is the second best. And what about third best? Well, it must be among these 3 guys. Basically, you have a frontier of candidates for the next best. And each iteration, you take the best of these candidates and then replace it with the 2 shoulders or successors.
Why do you need to add the 0.16?
Which one? This one, right? So yeah, there's a better way to do that. So you say, okay, when I replace the 24, I only actually need to replace with the 18, right? 16, right? But that requires a little bit more work, a little bit more, I mean, improvement. But the general way is just replace it with the 2 shoulders. I mean, you are guaranteed to get the best answer. Although your way is a little bit better, but yeah, actually, it improves the constant a little bit, but not the complexity. So it's a very good point. Yes. Now the third best is 20, and you replace it with the top 2, the 2 shoulders. And now 16 is already in the heap, so you don't push it again. You just push the 15. So you basically keep a heap or priority queue or whatever priority queue you would like to maintain the candidates. So this way it's k log k, because you only need k iterations. Each iteration you pop 1 guy, and you can stop when you find the case best, right? You don't even need to worry about what's here. You don't even calculate them. And you need log k to maintain the heap in each iteration. So it's k log k for each hyperedge. So it improves.
But if you keep track of which ones you have popped up, it's only k, right? K times.
What do you mean?
If you don't, you only pop up so you keep track of the ones that you popped up in each list, mm-hmm. and you only comparison the head of the list each time.
Yeah, but you need to, first of all, you need to extract the best of the heap.
Right, so if this is just like you merge 2 sorted lists.
No, no. So this candidate is not sorted. Yeah, you just maintain a heap or priority queue, and get the top one is log k time. So that's excuse me. So still not the best, because we're doing a lot of waste of work, because we calculate in the previous N1 we calculate the top k from each hyperedge, right? But what we really need is the top k for this vertex. At the end of the day, you don't even need to know all these k guys. If you just can get the top k for this vertex, then you're good. So instead of doing them sequentially, can we do them simultaneously? So of course, by the same idea, you know that, for example, this vertex has 3 hyperedges, and each hyperedge, you know, there's a square as before. Now you know that the first best of this V must be one of the first best of each hyperedge, right? So here k is 2, meaning you only top 2, and d is the degree or incoming degree for this vertex V. So d is 3. In the case when d is larger than k, you can throw away the useless hyperedges. Say here, the 32, the worst of these 3 guys, is never going to be used in the top 2 candidates, because so we know that among these 3 guys, this is the third So this guy has no chance to get into one of these two slots. And all these guys in this square are no better than this guy or worse than this guy. So if this guy has no chance and all this square has no chance at all, so just delete it. Now you have two guys, right? You know that this 42 is the best, and what's the second best? Well, as before, it's among these three guys. Basically replace this with the two shoulders. But now you have an item level heap. You have a kind of more global heap instead of a hyperage specific heap. And you still do the same thing, like extract the best and top two. And now you have the second best. Okay, now you are done. Then you don't even need to worry about all these guys. You don't calculate them. So this improves a lot, significantly from the previous algorithm, but still not perfect, because we're still calculating the top k derivations for each vertex. But at the end of the day, we only need the top k derivations for the target vertex, right? So why bother to calculate to waste time for intermediate vertices? So take a step further, and you notice that the progression from algorithm 0 to algorithm 2, the central theme is that we delay the calculations until really needed. That means we are lazier and lazier. That's really kind of on-demand computation. And we have larger locality. In algorithm 1, 0, we look at each hyperedge at a time. Algorithm 2, we look at all the hyperedges incoming to one vertex. And in algorithm 3, we look at the whole hypergraph at a time. Okay. So algorithm 3, the lazy offline algorithm, has two phases. The first phase is forward, basically do a normal first best search until the final item. And this is nothing different or very similar to the first best Viterbi algorithm. One thing different is we construct a hypergraph of packed forest along the way. I mean, in conventional Viterbi, first best Viterbi, you don't need to keep track of the non-optimal back pointers. You basically keep the best back pointer for each item, right? And can throw away all the alternative back pointers. But now, in order to recover the second best or whatever, you need to store the alternative hyperedges to each vertex. But time complexity-wise, it's the same, because you visit these hyperedges anyway, right? And the recursive backward phase starts by asking the final item, what's your second best? And the final item cannot decide at this time, because it has to ask its parents and basically propagating the question to grandparents and blah, blah, to the leaves. And then once you get the second best, you ask, what's your third best? So here's the demo. So S17 is, as I said, is final vertex or target, and has three hyperedges. And in the first best phase, you know this hyperedge is the first best. Okay, that's you already know. Now K is 2 and D is 3. You can as well just throw the worst hyperedge. Right? Basically, nothing here. We've got to make a slot into these two slots. Now you start by asking the question, what's your second best? Well, so basically it's either this one or the second best along this hyperedge, right? So or same as asking what's your successor on this hypergraph? Well, it must be either these two guys as before. So you know that my second best must be among these three guys, just as the same as in algorithm 2. But question.
Sorry.
Yeah, but the critical point is you don't know these two guys yet, because in the first best phase you only know the first best of each item. That's the difference from the algorithm 2. Algorithm 2 is forward, so you know everything. Now, what can you do? Well, because I don't know the second best of MP13, then I basically ask the same question to my parent as well, right? So I ask, what's your second best to these two guys, and they will propagate this question to the leaves.
So maybe I misunderstand, but I don't see how this is different from doing a star search.
Okay, great. So in speech world, people do this backward for the top k derivations, right? But the difference between speech world and our parsing world is that the speech world is largely finite state. So the underlying structure is a graph instead of a hypergraph. And now, because we're doing parsing or syntax-based translation, we have hypergraph where you can combine, or basically an and/or graph. Basically, we can combine two vertices. It's not like one vertex and point to another vertex. Several vertex point to one vertex. So you have a problem of combination, which is here like a square, so that you combine AI and BJ. That's not in the speech world. It's not in the A style.
I don't think finite state has anything to do with it. So when you do the forward-backward pass, when you do n-best extraction using A-star algorithm for HMMs, right? You have a forward pass, one best. You have a backward pass, one best. Actually, no, you just do the backward pass, one best, and that gives you the optimal continuation from every point to the end of the graph. And then when I start asking, okay, so what is the next best? You have all those partial hypotheses in the stack, pretty much what you have here. And then I say, okay, well, give me the next one.
Yeah.
And I really, maybe we can take it offline, but it seems that they're very similar.
Yeah, the idea is similar. Basically, we're extending it to the world of hypergraph, where basically you have combinations, which, is not in the case of.
Yeah, well, each combination is a hypothesis that's going to be in the stack, in the A-star stack.
Well, that means you transform the hypergraph into a conventional graph in beforehand.
Well, sure, I don't know. I mean, a hypothesis can just be a hypergraph, no?
Yeah, maybe we can take it offline. But, okay, so yes, now recursion goes up to leaves that by propagating the same question, what's your second best? And then it will basically backward reporting numbers of second best to these two items. And now you know the second best of, now you know basically all these three candidates. And now you can say, okay, this is my second best. And if you want more, then you can ask more, what's your third best? So this is the idea of algorithm 3. So there's an alternative implementation suggested by Jason Eisner. Basically, in the forward phase, as I said, in forward phase, you have to keep all the hyperedges. You have to construct the whole hypergraph. But sometimes your search space, your hypergraph is too large, especially for translation, for example. Then your memory is not sufficient to do that. But we can do something clever. We can only keep the best hyperedge as in the normal one best Viterbi. But the backward phase recover all the other hyperedges on the fly. So when you ask this final item, what's your second best? And it only has the best hyperedge, but it can recover the alternative hyperedges. Although this is really a waste of time because you already visited these hyperedges in the forward phase. You're basically doing it again. Basically, it's trading time for space. So you then ask this one, and it can recover all the hyperedges. Okay, so here's a summary of time complexity of these algorithms. We start from a first best algorithm, which is linear in the number of hyperedges. And then naive algorithm is k to the a, where a is the array. In CKY is 2 because we're binary, doing binary grammar. And algorithm 1 improves it to k log k, but still multiplicative overhead. Algorithm 2 is a dramatic improvement because it improves the multiplicative overhead to an additive form, right? And algorithm 3.
Does V there mean the vocabulary of the sentence?
No. Sorry, V means the number of the vertices. Yeah, basically it's how many items do you have in the chart. So number of non-terminals times n squared because you have 2 indices, right? And, like BP17. And E is number of hyperedges, and D is the size of derivation. Basically, how many nodes you have in the tree, in the parse tree. It's linear in the end because if you have a sentence of n words, then you have the tree is also size linear to n. Algorithm 3 improved from algorithm 2 basically by changing this V to D. And D is really, really small. It's like linear, and this E is cubic. So in practice, this E really dominates. That means as long as you don't have until you have very large K, the complexity is still not much different from a single best search, which is order E. So, and locality is from hyperedge to the global hypergraph from all, through all these diagrams. Okay. So
if I look at algorithm 2 versus algorithm 3,
2 versus 3.
So it's still E that dominates.
Mm-hmm.
Right?
And
so
yeah.
From 2 to 3.
Yeah, it's only the overhead, this part. Because this E, you cannot do anything about it. Even in first best, you have to do this E anyway, right? So this E is kind of inherent in the problem. You cannot improve it.
So it's still cubic time.
It's still, of course, because we're doing something more. We're doing k-best parsing. Parsing is cubic. When we're doing k-best parsing, we basically want to minimize the overhead. And we cannot improve the parsing algorithm itself. So that's our objective is only to make like computing the top assigned parses not much different from computing the first best parse. So that's what we'll be showing in the experiments. So we have 2 experiments.
Can I ask a couple of questions? So in the forward pass, are you still storing only the k-best hyperedges for each target node?
You mean algorithm 3?
In 3, yeah.
Yes. We store, because we only need the top k, we only store the top k hyperedges. Although we can store all the hyperedges, then that be the generalized JM algorithm, which is a little bit different, a little bit slower than ours, but it's not much slower. You can store all the hyperedges.
And so does the k log k come in because of that's the cost of maintaining the heap?
Right. Yeah, all the k log k comes in maintaining the heap because the insertion idea among all these algorithms are very similar, just maintaining a heap of.
So what's little d?
Oh, d is the degree of incoming degree. That's how many hyperedges do you have? Basically, yeah. So in case where d is much larger than k, then we are much better than the generalized Jimenez and Massal algorithm. Okay, so experiments. So first, the coding specal parser on the pen tree bank. So we implemented our algorithm 0, 1, and 3 on top of the BKL parser and recorded average wall clock time per sentence on section 23. So here the x-axis is k. So this means like computing the top sound parses, and this is time. So we see that, and this is log scale, by the way. So 3 is much faster than 1, and 1 is much faster than 0. And 3 is nearly kind of stayed the same because the complexity is E plus D k log k, where E dominates. The time for computing the first best parse is nearly most of work you have to do. That means we have very little overhead computing the second best, third best, fourth best.
Is there a reason you didn't run 2?
Because 2 is intermediate and use a lot of memory. And memory-wise, 2 is bad actually. Actually, we didn't. I made a slide of space complex comparison. Actually, algorithm 3 is more space efficient than algorithm 1 because oh yeah, we'll take it up later.
So, what is the average sentence length there?
Average sentence length is like 23 in the tree bank, 23 words, 22, 23 words in tree bank. Section 23. It's like distribution from 1 to 65. The maximum length is 65, but most of sentences are less than 40 words long. So besides efficiency, we also talk about accuracy. Because our search is more efficient, we can use less pruning, and the quality of the output will be a little bit better than the naive methods. That's our hope. So we compare Oracle Reranking results to measure the quality of our output. So what I just talk about what's Oracle Reranking. Basically, if you have a first best for one sentence and compared to golden standard in the tree bank, it might be like 89% accurate. And if you relax it to the top k parses, in the Oracle, the best may be 96, and you also get something very bad. So Oracle Reranking meaning pick the best parse according to golden standard. It's kind of cheating because in real ranking you don't have the access to the golden standard. You basically just compare these guys and pick one, say maybe this guy, and but Oracle Reranking also makes sense because it's the upper bound of any real re-ranking system. And also, if you get good for Oracle Reranking, then you have the potential to get good real ranking results. So this is the Oracle Reranking curve. We compare ours. Our curve is this line. Compared to Chuck and Johnson, this dots, and this is Collins' 2000 Reranking paper, and this is Rand Parkey's earlier parser. So Chanyak's all above us because they start from a different parser, where the first best of Chanyak parser is already 1.5% higher than Collins' parser. So it's really not a good comparison. So the real comparison is between ours and the Collins because they are based on the same parser. So we see that as k goes larger, our curve still improves. That means we can get better and better from larger and larger k-best list. But Collins' curve converges at around 50. And the reason is explained in this slide. So another plot is done by drawing the average number of parses for sentences of given length. For example, this guy is, so this point it means on average how many parses do you get for a sentence of 30 words long? Okay? So intuitively speaking, as sentences gets longer, you get more and more parses. Actually, it's exponentially more parses as the sentence goes longer, right? Then why does Collins' curve actually drops off after like 40? So it should go higher. And basically, but our curve goes higher, and we have the k equal 100, so it cannot exceed this ceiling. So the reason why Collins is like this is because he has the very aggressive pruning in the first slide. So what he did is a hard beam width, a hard cell limit that is only at most 100 items can be in a chart cell. A chart cell meaning all items with the same span. So all MP or VP from 1 to 7. So that way he prunes a lot of potentially good parses, and at the end of the day he has difficulty recovering a good parse. And in some extreme cases where sentence is extremely long, like 40 words, 60 words, he cannot recover any parse at all. That means he gets no parse. So that's 0.
So I think historically people used to report precision and recall on sentences less than 40 words, right?
Yeah.
So that would explain this.
Exactly. So yeah, that's correct. So this part of the corpus is only 7%. So Collins got the majority right. Majority not as good as ours, but not too bad. And if you see very short sentences with less than 10 words, these two curves actually match exactly well, very well, right? That means for short sentences, because the pruning doesn't do that much wrong. So I mean, it's good. But as soon as it gets longer and longer, the pruning effect becomes more apparent.
It would be interesting if you plotted just below here the distribution function, the cumulative distribution on sentence length, just to see how much of the corpus.
Yeah, exactly. A very interesting idea. Yeah. So the majority of the corpus of the Penn tree bank will lie between 20 and 30 words long. So, yeah. But let's also suggest that Collins' Reranking results did worse on very long sentences. But yeah, so his less than 40 words result is much better than the whole corpus. So now we shift to machine translation. So here is so here David Chen implemented these algorithms on the higher decoder, algorithm 2 and 3. And this is the average decoding time excluding the first best part, which is the dominating part. So these two curves also, reconfirm our parsing result. But what is more interesting is how do you use k-best translations in machine translation. So there are at least 2 applications, for example. In the Hiro system, David uses 100 best translations basically to tune feature weights because he has a log linear weight model, say language model, translation model, length penalty, blah, 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 like say 10 features. And how does he tune the weights and uses the minimum error training or max blue training by Franz Zock, which requires a k-best output. So that's one application. And the other is in the ISI syntax-based translation system, where I worked for the summer, for the past summer for an internship. So their way is, so their problem is they have difficulty integrating the n-gram models in the search, in the decoding part. So an easy approach is to just do the decoding with translation model only. And they get, say, they, for example, output 25,000 best translations using our algorithm. And then rescoring or re-rank these 25,000 translations with a trigram model. So this helps a lot. So their baseline translation model only decoding is 24.45.
Does that include a syntax-based language model?
No. There's no language model at all, it's just translation model. Since the evaluation metric is blue, if you don't have n-gram models to smooth the output, you get really miserable output. If you do a trigram re-ranking on the 25 best translations, you suddenly get 10% of 10 group points improvement. That's really significant. But still, this is not perfect because you prune away some potentially good translations during this search, this stage of search, so that later on, although you have so many translations, none of them is good. Then you don't have a way to recover using the trigram re-ranking. So the better way to do it is to integrate n-gram models in the search, which.
Sorry. So, what is the Oracle there?
Oracle? Oh yeah, we don't have Oracle. Sorry, yeah, that's a very good question. I don't know the result of their Oracle, which I would guess some 40 or something. I don't really know their number.
So you guess 40?
I cannot tell.
It's not trivial to do an Oracle solution because you can't do it by picking just, or you can't do it a sentence at a time. Because of the blue that gives zeros if you're missing, if you don't have any forward grids like that. It's really messy. Chris Quirk has been trying some approximations to find the Oracle score.
Yep. So if you integrate the n-gram model, trigram model, using a so here's something that's not actually in this talk, which I mean, if you guys are interested in talking to me, I would talk that how do you integrate n-gram models in the syntax-based translation system, which is also very difficult for Chris Quirk's system here. So the naive binarization way, because you have to use the CKY decoding, the CKY parsing algorithm, so you have to binarize the grammar into some binary form. Naive binarization, we got this, which is better than trigram re-ranking. And what I did in ISI is synchronous binarization with trigram, then you get 38.4. If you compare to Franz Zock's implementation at ISI, so that's what ISI submitted for the NIST evaluation entry. That's alignment template approach, that's 37. So that means the syntax.
So is this before the bet between Daniel Marcu and Franz Zock?
Yeah, that's
because he lost that bet. Right?
Yeah. So yeah, exactly. So in NIST evaluation, the main entry that ISI submitted is this number, is this alignment temperature approach. Then their syntax system is like this when the NIST evaluation. And these results are before.
So this is work you did last summer.
No, this past summer.
This past
yeah,
summer, which is after the
NIST evaluation. Yeah, exactly.
Also, that's Franz's system that he left behind at ISI, not his new system at Google.
Yeah, exactly. So this is the last update when he left. It's the stage when he left ISI.
So do you think they're going to swap the shirts next time?
Yeah, exactly. So, yeah, so that means in the.
I'm afraid 200 billion words of target language training data is worth more than what.
Yeah, exactly.
So maybe not.
Yeah, I mean, if you have the same amount of resources, then we did beat Franz Austin, but it's not. Okay, so yeah, this is my current research. So to wrap up, we first formulated a monotonic hypergraph formulation, which is very general, and defined the k-best derivation problem. And because the framework is general, then we can make it widely applicable to a lot of problems, say syntax-based MT. And we have k-best algorithm, which the last one, the final algorithm, is pretty fast. And our experiments show that not only the efficiency has been improved, but also because you can do a more effective search, your accuracy is also improved. So for a little bit of future work, so all this talk is about k-best Viterbi algorithm, where you proceed along fixed ordering, fixed acyclic ordering. But we can also do k-best A star, which, say, for example, Dan Klein has A star parser, and we can make it a k-best A star parser. And this is also this is of great interest in the machine translation community, because I know some people are already trying to do k-best A star decoding for machine translation. Not A star, k-best A star, but they're doing A star decoding for machine translation for the syntax-based systems. Other people have done A star decoding for phrase-based systems, but that, as I said, that's basically a finite state world, which is a graph. But A star for syntax-based or for the tree world is based on hypergraph. So that's a bit different. And we are formalizing dynamic programming, the optimization part, into the hypergraph search problem, because we have the monotonic weight functions, which is saying the optimal subproblem property in dynamic programming. And we have to do real reranking to show that whether this Oracle improvement really pays off in real reranking. So Chernyak already implemented our algorithm 3, and they are also doing ranking with larger k, basically because now you have you have, say, ASAN translations. Then you cannot use the max entropy reranker. You have to use an online reranker, say perceptron algorithm. So otherwise your memory isn't sufficient. Okay, so that's basically it. Questions?
Are there any questions that people? Well, I think people might probe you more in the discussion afterwards. So I know that you're lined up to have lunch with you here. So thank you. Yeah, so we have implementation of algorithm 1, which he was saying that which I've given a number because it's more straightforward. But Jan was saying that actually algorithm 3 is
Am I supposed to have lunch with him?
So it's an interview lunch, you can go outside.
And that's at noon?
Well, from the end of this talk.
From the end of this talk?
So I told him that if he finished earlier, it would increase the probability that he would take him somewhere interesting.
Right, so we have to be back by what?